So I'm talking about geolocating jammers and spoofers. So hopefully, although you couldn't hear me, I was talking through the contents here. So we're going to look at different geolocation techniques, time difference of arrival, and so on. We're going to look at geolocation of spoofers. We're going to look at urban geolocation, which is quite a different problem and needs some very modern techniques. And then just at the end, touch on augmented reality. So it's a bit of a whirlwind tour, but let's first talk about what we mean by the geolocation problem. So it's essentially, you can think of it as an inverse to the navigation problem. So if you look at the left-hand diagram there, that's what we mean by satellite navigation. So you've got a single user in this case that's navigating from a variety of transmitters, in this case satellites. And the geolocation problem is the inverse of that on the right-hand side, where we have in this case, a jammer or a spoofer, some kind of interference, and we're going to use an array of sensors to try and receive that signal and geolocate it. So it won't come as any surprise, I guess, that a lot of the techniques that we use in navigation, particularly in GNSS and radio navigation, a lot of those techniques can be reused for the geolocation of jammers and spoofers. So I've drawn multiple sensors here for geolocating the interference, but of course we can do it with a single sensor as well, which we'll touch on briefly. So Mark's already covered this in great detail, so I'm just going to touch on it briefly. Some of the common types of interference that we can encounter. So the top left one there, these are spectrograms. So this is time along the x-axis on the bottom and frequency up the side. So the first one there is a narrowband CW jammer. And that's sort of typical of self-interference from local clocks or from equipment nearby that's gone wrong. The chirp jammer in the middle there is the one that's very typical of your sort of personal privacy devices, the mass market jammers that are around. Some of the other ones, the broadband noise and the pulsed versions of those jammers, they tend to be a little bit rarer in I guess, everyday life. They're more typical of state-sponsored jamming attacks. The reason I'm showing you these again is because the type of jamming can influence the techniques that we use to geolocate it. If you're geolocating a narrowband jammer, you can tend to need very different techniques from geolocating a broadband jammer, for instance. Okay, so let's look first at time difference of arrival. So what I've got in this picture here is there's a little cross somewhere on there, which is representing the position of a jammer in this case, and there's little red circles are positions of sensors. So this is an XY distance plot, so you can think of it as looking at the ground from above. And I'm doing this in 2 dimensions to make it a little bit easier to sort of visualize what's going on. With time difference of arrival, what we're doing is taking 2 of those sensors and looking at the relative time delay, so how long it takes the jamming signal to arrive at one sensor compared to the other. And if you measure that time difference, you can plot something that looks like this. It's a hyperbola, which is all the locations that jammer could be at. And as you can see, that curve goes through the jammer position. And in this case, we've got 4 sensors. So there are 6 different pairs of receivers which are possible that we can use to measure a time difference of arrival. And if we plot those other ones, we'll get a curve for each pair of receivers. So if we add all those in, we end up with something that looks like that. So we've now got 6 curves on there representing 6 different time difference of arrivals. And as you can see, hopefully they intersect. And that intersection, if everything goes to plan, is going to be where your interference source is. And now I've just got a little 3D picture on the bottom there, because of course this is actually in reality a 3D problem. I've shown it with 2D lines. In reality, you get 3D hyperbolic surfaces. So that can be used to geolocate the jammer in 3 dimensions. So that's time difference of arrival in a nutshell, is to geolocate based on the intersection of all these hyperboloids. And how do we do that? Okay, so this is the technical theory behind it. So you look at your sensor pairs. In this case, we've got 4 sensors, and we want to find every combination of 2 sensors. So we use something called the binomial coefficient, which just means we're looking at all the different pairs, which in this case gives us 6 sensors. And then we take the received signal. So in this case, our jammer is a broadband noise jammer. So this is a 30 megahertz wide broadband noise signal, which looks like that. What we do is we take those received signals and we cross-correlate them. Okay, so this is a little equation here for the people that like that. All it is it's showing the correlation of 2 signals. So we've got the signals X and Y from 2 different receivers. We're multiplying those together and sliding them past each other. So that's just a cross-correlation function. Okay. When you plot that cross-correlation function, it looks something like this. So we've got 6 different cross-correlation functions, and we're plotting those. And when you plot those, you end up with these 6 peaks. And those peaks are the bits we're interested in. And if you look on the x-axis, that represents time. So what we need to do is look at that x-axis and find those time differences. So in this case, you can see there's a purple one, which has got a time difference of very close to 0. And that means that the jammer is almost directly centered between those 2 sensors. And others have different time delays. And once you've got those time differences, you use those to plot your hyperbolas that we've just seen. And that can then you look at the intersection of those, which is not always obvious. In this case, the diagram looking at that, it's quite obvious where the jammer is. In reality, in a lot of circumstances, they don't intersect quite as nicely as you'd hope. So we have to do some other things, which we'll come on to. So that's time difference of arrival in a nutshell. Now, it does have some problems, time difference of arrival. It can be very, very accurate, but here are some limitations of it. I'm not going to go through them all in detail. I'll just pick out some of these. If you look at number 2, we're measuring times. So we need to be able to have very accurate time synchronization between the sensors. And what do we normally use for very accurate time? Well, of course, most people like to use GPS or GNSS. And if we're trying to geolocate GNSS jammers, then we've got a problem because the chances are our sensors are going to be jammed, so we won't have the timing accuracy that we need. So the first rule with TDOA is don't use unprotected GPS as the timing source. You need to either protect it with an anti-jam system or use a different mechanism for determining time. Other things like number 1, the geometry of the sensor locations. Ideally, you'd like to have a good spread of sensors around the target in order to get a good geolocation. Other important ones, things like number 5 is, I mentioned signal bandwidth. Time difference of arrival is no good for narrowband jammers because you don't have that, you can't get any decent cross-correlation function out of it without any bandwidth. So it's very good for broadband jammers and for chirp jammers and things like that. Not so good for your CW jammers and other techniques we can use for that. And again, number 6, this technique is very good in open air environments. Once you get into a crowded city environment, an urban environment, this technique starts to fall apart very quickly. Okay, so that's TDOA. Let's look at another technique, which is angle of arrival. And this is the other really common one. And this is often referred to as direction finding. And essentially, there's lots of ways of doing this, but essentially what you're trying to do is, given a couple of sensors or several sensors, is you're trying to measure the angle of arrival from that sensor to the jammer. So in this case, we've got 2 sensors, A and B, and we're measuring the direction of arrival of that jamming signal or that spoofing signal to each of your sensors. And then once you've got that line of bearing, you can then do triangulation in this case and geolocate the jammer in that way. So there's lots of different algorithms for this. They all have posh names like Music and Esprit and IMP. The common one, or the one that most people seem to like to talk about, is called Music, which stands for multiple signal classification, and that's a very well-known technique, what we call a subspace technique. So let's look at that in a little bit of detail. So here we've got another bit of a technical slide going on here. So if you don't understand the maths, that's fine. Don't worry about it. What we're doing is essentially we're taking the signals from an antenna array, and so a number of antenna elements that are carefully phase aligned. And what we do is we form what we call an eigen decomposition of that. And what that does is that separates out a number of signals, jamming signals, from the background noise. And then we can separate those subspaces out, and we plot something called the music spectrum. If you look at point 4, there's a nasty looking equation there. If you're into linear algebra, you might recognize that as a projection matrix. So what we're doing is we're projecting the signal subspace there. Okay, and then you look and find the peaks of that function. So if you don't understand that maths, that's fine. But what I would like you to do is look at those 2 pictures. You've got one of those pictures which is called eigenvalues. And what that's telling you is you've got one very strong jammer. So it's a bar graph that's telling you how many jammers you've got and how strong they are. And the other picture there is what we call the music surface. And what that's telling you is where the jammer is in this case, azimuth and elevation. So it's plotting a jammer that's at about 160-degree azimuth and 90-degree elevation. So that surface gives you hotspots of what directions jammers are coming from. In this case, there's just one jammer, but there might be several. So that's the music algorithm that does angle of arrival. Okay, so what does that do for us? Let's go back to that same scenario again, where we've got 4 sensors and a jammer, and we can plot that line of bearing. So from one of those sensors, we get a line of bearing that goes hopefully through where the jammer is. And then we plot the others. And again, we get a number of lines that will hopefully, if everything goes to plan, will intersect and give us a geolocation on that jamming source. So angle of arrival has its complications, but it also has some great benefits over the previous technique, time difference of arrival. With angle of arrival, we don't have any requirement for timing synchronization, which is great. So there's no dependency or hidden dependency on GNSS for doing this. And it's also good for all types of jammers. It works against both narrowband and wideband jammers, whereas TDOA has limitations on the type of jammer it can geolocate. The downsides of angle of arrival is that it does need a more complex antenna, an antenna array with some associated electronics. And it also needs what we call an array manifold, which is essentially a highly accurate way of calibrating the array and understanding its performance. So that's angle of arrival. Just very briefly, there are some other techniques which are out of scope of this short presentation, but things like frequency difference of arrival, that's a really good one where you can exploit Doppler shift, which is really good if you happen to have a jammer that's moving, or if your sensors themselves are moving, and you might be sensing from an aircraft, for example. Others are PDOA, and there's two different definitions of PDOA. The correct one is phase difference of arrival, which is also known as long baseline interferometry, which can be very, very accurate indeed. The other technique is power difference of arrival, which is basically looking at the received power, the differences in received power signal strength at different sensors, which is very easy to do, but generally it's quite poor accuracy. But by combining all of these, you can get a better geolocation. Okay, so let's just think about moving platforms for a moment. What I've done so far is talk about a number of sensors that are deployed around your jammer that you're trying to geolocate. Of course, you can do it with a single sensor. So in this case, I've drawn an aircraft that in this case is doing a line of bearing. So it's doing angle of arrival. But we could also use some of the other techniques like frequency difference and phase difference of arrival. And as that aircraft flies along, we're going to get over its trajectory multiple lines of bearing. So you can essentially geolocate using a single sensor. That could be an aircraft, it could be a drone flying over an urban environment. And what's nice about that is it helps to average away some of those errors, because as the sensor's moving, some of the errors that it encounters will change over time. So those errors naturally average away. So that can be a very powerful technique. Okay, so that's enough about the measurements themselves. How do we actually go about geolocating? So we've got a set of measurements, we've got a set of perhaps time difference of arrival curves, we've got a set of angle of arrival, lines of bearing, we might have some other measurements. How do we actually geolocate those? So let's look at a real scenario now. So this is in Hampshire, and hopefully you can see on that slide there are sort of 4 pale green dots, which are these sensors from the previous examples I was giving you, but overlaid onto a real map this time. How do we go from some measurements to the geolocation? Well, let's just plot those time difference of arrivals again. So those are the time difference of arrivals, and already you can kind of see where the jammer is going to be in this case. It's very close to Roke Manor, where I work. And let's also overlay the angle of arrival lines of bearing on that. And again, that gives us an even stronger indication that we know where this jammer is. But we're quite zoomed out on the map at the moment. If we just zoom in a little bit onto that, this is what we see. And so now it becomes a little less clear where that jammer is. We know it's somewhere around, and it's probably going to be in that field you can see there. But if we wanted to get a very more accurate geolocation on that, it becomes quite difficult from those lines to work out where it is. And especially if that was an urban environment, if you're wanting to pinpoint to a particular building or a street, that's going to get quite difficult. So how do we improve on this? And this is where we need to start bringing in sensor fusion techniques. And I'm going to introduce something now called the discrete probability density. So we're going to go a little bit technical again, but all we're saying here is, rather than, in this case, show a line of bearing, turn that from a single line into a probability density. So rather than saying it's along this line of bearing, and that's all it is, we're going to turn that whole picture into a probability density. So we can say it's most likely to be here. And if you viewed that in 3 dimensions, what you're getting is a sort of a ridge of probability, sort of a Gaussian distribution. And you can do that analytically with something called the Kramer-Rayo bound, or you can do it empirically with estimated statistics. And we can do that with each of our measurements. So let's just do that now and look at all those. So the first 4 going along the top are your lines of bearing from an angle of arrival technique. And the other ones, the last one on the right hand side at the top, and the ones all along the bottom, are your time difference of arrival measurements. So those are your hyperbolas. And you can see at the ends of the hyperbola tails, they start to broaden out a little bit as you get further away from the focal point, if you like. But those are all probability maps. And if you remember your sort of high school maths and statistics, is how do you combine multiple probabilities? Well, you multiply them all together. So if we take each of those images and multiply them together, that will give you a new image, which will give you a probability map of where that jammer is. So let's overlay that onto our map. And there it is. If you combine all those images from the previous slide, you end up with a hotspot. And that gives you a really nice way of geolocating where that jammer is in a maximum likelihood fashion. So we can now see very clearly where that jammer is. And in fact, that is where the jammer was in this case. So we get a heat map, and we can take that one step further, which I'm not going to do now. We can then start applying things that we do in GNSS receivers. So we can start applying Kalman filters and particle filters, so we can track that, particularly if it's a moving jammer or moving sensors. We need to start applying tracking algorithms. But those are some of the basic techniques that we can use for geolocating jammers. Okay, just very briefly, spoofer geolocation, because this is in many ways a different problem, but also we can use exactly the same techniques again. We just have to do something. We have to do an extra step. So what I'm showing here in the top diagram there is a GNSS receiver. That's if you're familiar with GNSS, you'll recognize that as a GNSS correlator. So what we're doing here, you have to remember that a good spoofing attack usually sits below noise because it's trying to look like the GNSS signals. So unless you're very close to that spoofer, you may not see it at all with traditional techniques. So what we need to do is apply these GNSS correlators into our after our antennas before we do time difference of arrival or angle of arrival processing. So that diagram there shows a GNSS correlator, and the first part of that is an oscillator which is wiping off the carrier, and then you have the code generator. So we need to use the GNSS codes that we're interested in here. So we'd be reusing the CA codes or the Galileo codes, whatever kind of spoofer we're looking for. We need to be using those codes so that we can correlate on those. So what we do is to take that correlator and we put it after every single antenna that we're using in our sensor. And once we've got those and got the integrate and dump out of those, we can then apply our time difference of arrival or our angle of arrival techniques. So we do exactly the things we've just heard about, but we need those extra correlator steps on there as well. And that's what allows us to geolocate spoofers. Okay, we can detect and correlate on every single satellite, whether it's a real one or a spoof one. So it's important here that now we're looking at spoofers, we need to be able to differentiate between spoofers and real satellites, because we don't want to geolocate the satellites, we want to geolocate the spoofers. And one clue about spoofing is that it tends to come from the same direction, unless it's a very sophisticated spoofing attack. Unless it's very sophisticated, all the spoofing will come from a similar direction, and it will be a direction that the satellites are not expected to be coming from. Okay, moving on to something quite different. We've talked so far about time difference of arrival, angle of arrival, and various techniques that can be used to geolocate spoofers and jammers. Those work very well in the open air environment. Once you get to a situation like this, where we've got a complex urban environment, and we've got a jammer there, it becomes a very different problem indeed. So here we can see there's a jammer sitting somewhere in this city, and I've labeled that. And we've also got a sensor which we've plonked on the top of a building. And you can see that because of multipath and reflections off all these buildings and diffraction and retransmission and all these different propagation mechanisms, that the jammer will arrive at the sensor by several different paths. I've drawn 2 paths on here where it's reflected off buildings. And it also doesn't arrive from the direction you expect it to. So when we've got this kind of problem in the urban environment, it's rarely line of sight. You don't see the jammer directly. So that causes problems with our time difference of arrival, because the propagation distance is longer. So the times that you're measuring are going to be wrong. And also your angle of arrival technique is going to struggle, because the jammer will tend not to arrive from the direction of the actual jammer. It's arriving from the direction of the signal, which has probably been reflected. And also you end up with many correlated signals received, which can cause great confusion, because you're not just seeing the jammer once, you're seeing it several times from several directions. So how do we deal with this? Well, it needs a completely different approach if you want to do this in an urban environment. So let's look at how we do this. And we're getting now onto the state of the art geolocation, really. And the secret here is not to fear the multipath, not to treat multipath as a problem, but to exploit it and to embrace it. And so what we're doing here is looking at a received fingerprint, if you like. So the picture I've shown here is what we call a power delay profile. So this is an example jamming signal which is received over a period of time. And you can see as that jammer's turned on, we see an initial big spike, which comes from the closest path. And later on, we see another spike of a different shape, which has come from a further reflected signal, and so on. And so you get this unique fingerprint. And if that jammer was somewhere else, you'd see a different pattern there. So what we'd like to do is take our urban environment and create a database of all the possible fingerprints, which represent all the possible locations of that jamming signal. And that can be a really difficult problem because we don't want to go around and turn on a jammer at every point in London or a major city and see what the received signal looks like. But what we can do is we can use modern ray tracing. So we can get 3D models of urban environments these days. And those are accurate enough to be able to generate these power delay profiles and other received signal fingerprints for us. So we can use ray tracing to simulate what the received signal will look like and generate that database. So here's an example of a ray tracing model, which was modeling part of Coventry, the city of Coventry. And you can see it's a little bit unclear, but hopefully in that green and blue picture, you can see it's modeling all the reflections there from a jammer and a receiver. And what we've got there in the graph on the right hand side is kind of an impulse response, if you like. It's the fingerprint that we're receiving from that transmitted signal. So we can use ray tracing to do that for us, okay, and generate those set of fingerprints that we can then use. And then we can use machine learning techniques, which are very good at pattern matching, to come up with the most likely position so that when we receive a jamming signal for real, we can use matching against a fingerprint database. And there's a variety of techniques which I can't go into, but using some really state-of-the-art machine learning techniques to look at that and geolocate the jammer in an urban environment. Okay, so we're nearly done now. The last thing I'm just going to mention before signing off is augmented reality. Now these are videos, but for the purpose of the webinar, I've just showed them as still images. But we can, all the techniques I've talked about so far, whether that's angle of arrival, time difference of arrival, urban geolocation, all these different techniques we can use, and we can combine that with a video camera image. So we can start to do augmented reality. So what I'm showing in this case, on the left-hand picture, we've got a GNSS jammer that is standing on a table. So that little blue jammer standing on a table there. And what we're doing is from the sensor that this person is holding, they're doing angle of arrival techniques and getting a line of bearing to that jammer. And then we're just combining that with a video camera in live real time and overlaying a red crosshair onto that. And then as the person moves this camera around, and we can geolocate and see where that jammer is in real time. And the same with the picture on the right hand side. In this case, there's a cigarette lighter jammer in that car. And as that car drives into the car park, it's geolocating and putting a crosshair on where that jammer is as it drives in. So geolocation can be combined with video cameras, and augmented reality gives us a really powerful way of immediately seeing where that jammer is in a potentially crowded environment. Okay, I've talked about quite a lot in a very short period of time, so let's just summarize. There's a lot of different techniques available. Time difference of arrival, I've talked about, angle of arrival, and I've talked briefly about frequency difference of arrival and phase difference of arrival. They all have their strengths and weaknesses. None of them are perfect. And using a combination of techniques is usually a good idea, as is in navigation to use a combination of techniques. And you can fuse these together in various ways. You can just use lines if you want, but it's much better to use probability and statistics if you want to get a more accurate geolocation. And then we talked about urban geolocation. We talked about fingerprint techniques and using correlational machine learning to perform the geolocation. And airborne sensors are also very useful if we want to do urban geolocation, because we get less multipath when we're measuring from above in the air. And finally, we just touched on augmented reality as a very powerful technique for hunting jammers and spoofers. That's it from me. I'll hand you back to Claire. Thanks very much for listening.